Now in this video we're going to take a slower paced look at the three main ways that 555 timer integrated circuits are used, plus another one that I like. But in any case, so there'll be four circuits we'll look at. These are just the basic circuits. So right now the 555 timer output is high. We have this wired in bistable mode. So it's going to stay high until we force it low. So a low input to the reset pin sets the output low. So being bistable, there's two stable states. High, which we saw before, and now low. Those are the two stable states. It will stay low until we give a low input. It can just be a brief pulse or whatever. But in any case, that was a low input to the trigger pin, pin 2, and the output is high. And again, it's going to stay high until we force it low again. And now we'll look at the diagram I put together. So we got the 555 timer integrated circuit. It has 8 pins. When you look at the schematic diagram, you'll have the numbers there. So the pin number 1 is the top left pin, and you work your way down 2, 3, 4, and then however long the integrated circuit is, once you get to the bottom, you jump across. So we have 4 pins down, and breadboards push these out, by the way. And so in any case, we're over to 5, and then we work our way up 6, 7, 8. So hopefully that makes sense. And if you go to the 555 timer integrated circuit, and a lot of my diagrams, it shows the names of the pins. But on the schematic, you'll see numbers. So in any case, let's get to the circuit. We are not going to use pin 6. So we just have it tied to ground, as you can see right there. It's waiting for a high input. We put it directly to ground. That just makes sure that it doesn't do anything. And also, it's a good idea to have a capacitor across the integrated circuit to stabilize things, and a capacitor from pin 5 to the negative supply, their small value capacitor, to help stabilize things. But they're not crucial, so I generally don't add them into my circuits unless it's not working without them. So, in any case, we have that disabled. We have to power an integrated circuit, pin 1 to the negative supply, and pin 8 to the positive supply. So that is always wired up like that. So I'll rush through that in the upcoming circuits. Now we have the output, which it connects to ground really good. You get pretty much 0 ground, and it connects the output to pin 1. The transistor turns on basically and makes a direct connection. You have to go through more transistors and stuff for the high output, so you lose some of the voltage. But in any case, when the output is high, it's close to 5 volts, you can see that's why the red LED lights up right there, because it's going to ground. You have to have the voltage difference across it. Whereas when it connects to ground, then the blue LED lights up, because that's the voltage difference across there. That's what that means. So let's get to how we control this one. So let's say the output is high right now, low, sorry. Say the output's low, could be high too. But in case, if we press this switch, we connect to ground. Pin 2 and pin 4, so pin 2 is the trigger pin, pin 4 is the reset pin. So trigger sets it high, and resetting sets it low. So the output kind of wants to be low. When it's resetted, it's low. We have the pull-up resistor just to make sure it gives 5 volts so that it doesn't do anything. It's waiting just for a low voltage. Hopefully that makes sense. With the switch open, that means we got 5 volts. And when we close the switch, then current will go through the resistor to ground based on 5 volts divided by 10 k ohms. But in case while the switch is closed, that's also a direct connection to pin 2, so it'll see 0 volts. And that will set the output high. Now, you release that, press this switch. Again, this one is active low, responds to it was really close to 0 volts when I measured before. With pin 2, it's 1/3 of the supply voltage or less. So we press that button, that sets the output low. Now, you may think, what if you press them both? Because each one of them wants to do opposite things. The reset pin is the most powerful of these three here when it comes to the signal. And pin 4 and 6 do the same thing. If they get the right input, they'll set the output low. But in any case, pin 4 sets the output low, 0 volts, no matter what, whether you're pressing the switch there to pin 2 or not. Now, again, to set it high, that's the trigger pin up there, and then we got the reset pin These switches kind of work their way out, especially when you first start putting them into the board. They might even fly out. And that's the threshold pin, measuring at pin 6. But we're not too worried about that. So, in any case, now it's low, and now it's high. It goes back and forth. There you can see our pull-up resistors. The way I wired this, I like to put the switches where we got that little bump there. Just kind of helps me guide things. And they're separated top to bottom, but this goes straight across. So if it was seated in the board all the way, which it is like half the time, then that's all one connection at the bottom. If I pull this out, then there's a gap between those two sides. So the bottom two are always connected, top two are always connected. And that comes that jumper going up to the reset pin, pin 4. And there's our 10K resistor going to the positive supply. When I press the button, those 4 separate rows are all connected with the switch when you press it, and gives us R0. So same thing there, just the connection is above. And so we got jumpers going to each side of those switches. When it comes to the output, so I'm pretty sure this is the same on all of the circuits I will show. You can see we got the output. So again, it connects to ground pretty good when it's low, like we see there. So 1K resistor, higher value because blue LEDs are naturally brighter than red LED. So that's going to ground, positive to ground. And then again, to set it high, that's the trigger pin. So these are good things to memorize if you're going to be making a bunch of 555 timer circuits. And so it does go through some more transistors and stuff, so it loses more voltage. Lighter loads, it'll have higher voltage. But in any case, that's the long lead, the anode for both of these towards the positive supply, short lead, the cathode towards the negative supply. 220 ohm resistor because red LEDs just don't get as bright. And now we'll look at the monostable mode 555 timer. So we already saw what's going on there. We don't need to look at that. We'll zoom in a little bit. One thing to note, we were looking at pin 4, the reset pin last video. We're not using it in this video. We're disabling the reset pin. So we just have it connected directly to the positive supply. And now we'll move back. So monostable mode, this is our one stable state with the output low right there. You can see that when I press that button, the output goes high for a period of time, and then it goes back to low until I force it. So it's stable unless I force it. But since there's only one state that it's stable, that's monostable mode. So that's with the 100 microfarad capacitor and a 10,000 ohm resistor. They are what are setting the time. So that was a 100 microfarad capacitor. Pretty sure I said that right. I shot this scene before and said this was a 10 microfarad capacitor. It's actually a 1000 microfarad capacitor. So 10 times the capacitance. That's actually why I'm reshooting this scene. That was a big mistake. But in any case, you're going to see that the output is high for approximately 10 times as much. So these are not high precision circuits. And also capacitor values can vary a bit. Kind of feels like it might be longer than 10 times, but I could be wrong. But in any case, that's what we got. So capacitor to negative supply right there. Let's zoom in to the schematic. So again, we already talked about the output for the most part. But in any case, we don't want to reset it, as I said before, so we disabled it. Put pin 4, the reset pin, to the positive supply. Instead, we're using pin 7 and pin 6. So pin 6 is a threshold pin. It's waiting for the voltage of the capacitor in this case to get more than 2/3 of the supply voltage. So like 3.33 volts or something like that. I can't remember the exact voltage. But in any case, it's waiting for 2/3 of 5 volts or whatever supply voltage you're using. 2/3 of that. Whereas pin 7 is the discharge pin. Sometimes it connects to ground. And an easy way to know if it's connected to ground, the output is low at that time. And so it is connected to ground right now, as you can see there, until we press the button. So let's talk about what's going on when we press the button. You need these two pins, at least pin 6, but if you're going to be discharging the capacitor, you also need pin 7, which generally you do. They are the timing pins for the most part. Also, you could connect pin 2 in the loop, but we'll look at that in the next video. So, in any case, the output is low. We press the switch. Also, as I said before, when the output's low, that's connected to ground. So capacitor's discharged. We press the switch. That sets the output high. It turns pin 7 off. Pin 7 is not conducting. So neither pin is conducting. This one never conducts. But neither pin is conducting. You can see the path for the capacitor to charge. And so as I said before, it's waiting for 2/3 of the supply voltage. And so higher values take longer. Lower values are quicker. You can go really high on one and really low on the other one, or vice versa. To get your timing, you can adjust it. There's formulas too for it, but we're not going to worry about that. We're just looking at the basic principles of what's going on. So you can see that that's how it charges, and this might be a bit high of a value for this circuit, because once it gets to 2/3 supply voltage, that connects to ground, pretty much instantly, as does the output. So the capacitor discharges pretty much instantly. So you don't have to wait for this to reset. You can just keep timing it as much as you want. There we go. And because that's shorter, right when it jumps back. There's no waiting period for this one. Once the output's low, it discharges capacitor instantly. You can jump back into action as soon as you want. So I think we covered that pretty much over there in maybe more detail than you even wanted. So a 10K resistor for charging the capacitor, but right now the output is low. It's connected to ground. So any current that gets through the resistor just goes to ground. Any charge the capacitor had just went to ground, and it's being held to ground. There's no way for the capacitor to charge until we press the button again, as we saw before. Hopefully you could see that. And now we have the Astable mode, which I wrote there. We already covered everything going on over there. A reminder, you always have to power the integrated circuit. Pin number 1, negative supply, 0 volts, and then pin number 8 to the positive supply. We're using 5 volts at this point. But in case these two pins are looking for 1/3 of the supply voltage or less for pin 2, and 2/3 of the supply voltage or more for pin 6. We have them tied together right there, and we have pin 4 tied to the positive supply so that it isn't doing anything. We don't have to worry about that one at all. So just kind of a quick review right there. And so Astable, there's no stable state. I also put this capacitor up there before I forget, because if I bump the power supply, it will reset things. But there, it looks like it's holding steady, and as soon as it goes red, it you can see every time I bump it, like it puts the output low. So this is especially with this power supply, it's kind of important that I have a capacitor. Doesn't need to be this large to stabilize especially like circuits like this. So in any case, there we go. We got the output flipping between high and low. We'll come back and I can keep this stuff in view right there. As I said before, we already covered the other stuff. So we got them tied together. They're both monitoring the same voltage because they work on different ends of the spectrum. 1/3 or less, 2/3 or more. In between 1/3 and 2/3, the output just stays doing whatever it's doing. And so when the output is low, like when I first applied power, that's because the capacitor was discharged. It was basically 0 volts. And so it needed to charge. And that's actually a little bit longer, the first charge, because it goes from 0 volts instead of 1/3 of the supply voltage up. But in case, we got the 10K resistor for the timing, so we're getting about the same timing as the last circuit for each high and low. And so in any case, goes through that resistor. Now it goes through the diode. And a little current will trickle there. That's not a perfect conductor there. So I think it kind of eliminates the two of them when it comes to how much current is flowing. So just the 10K resistor, I think, sets the timing. Well, it charges. But in case it charges, its voltage goes up. When pin 6 sees 2/3 of the supply voltage or more, I think it's actually like 3.66 volts or something like that. But in any case, whatever it is, 2/3 supply voltage, then the output goes low and pin 7 connects to ground, as I said before. That lets the capacitor discharge, and any current that goes there just goes directly to ground. Doesn't affect the timing at all. The capacitor cannot discharge through the diode. That's reversed bias. So you can see the gray band, the cathode is touching the positive side of the capacitor. These are polarized capacitors, by the way. I didn't mention that before. That side needs to be more negative. So if you ever measure that with the multimeter, That one will be more positive. That one will be more negative. You can damage these if you reverse charge them. If you reverse charge them with too high of a voltage, they can burst. That's why they put these little slots there to vent gas. And but I've never had the one of these vent or anything, or maybe, you know, I fried it, maybe it leaked some gas, but I never had one blow up or anything. It's not that common, but I've seen videos of people do it if you want to look for it. So in case we talked about the charge, I got distracted there, and then when it discharges, it just goes through that resistor because it can't go through the diode. So when the output is high and the capacitor is charging, that is that value resistor and the value of the capacitor. Once it goes low and discharges right there, then it's this value of the capacitor and that resistor right there. So you can make one or the other larger, actually like both resistors larger or the capacitor larger if you want to slow it down 10 times. And I think that's stray signals right there holding that. That's kind of odd. It should have picked one or the other. But in any case, let's put the capacitor. That's like 10 times the value right now. And again, if I bump the power supply, I'm going to do it right when it goes red. Then the output will go low right away. So it should stay high in the same amount of time, but I bumped it and that threw it off. And so I can put this capacitor to the supply rail right there to knock that off. So just thought I would add that. But in case, we already saw before with the 100 microfarad capacitor there, it flipping back and forth. And we're going to see that again right now. And so yeah, I explained that process. For this one, I just made a little jumper right there with my wire cutter and my wire stripper. Pretty easy. Just I have 22 gauge wire, and I made that there. So I think we covered everything. Let's move on to my next demonstration circuit. And finally, we have what I call the Schmitt trigger inverted circuit. This is not one that usually see listed as one of the main circuits. Usually it's just these other three. But this is a circuit I think would be a good fourth one to add. So we already covered all the stuff you see to the right there. We aren't quite introducing anything new. We have pin 6 and pin 2 tied together. They are both monitoring the voltage like we said before. But here we have a trim pot. So we can set a voltage. Again, this is just a signal. They don't let current in or out. They're just looking at the voltage. But at some point we had less than 1/3 of supply voltage. Maybe we still did. And kind of bumping the power supply and stuff. Maybe I should add that capacitor again. But in any case, there you can see the output is high because we have a low enough voltage. So I got to go up to about 2/3 of the way, and there you can see the output went low. So that's as far as I can go up there. But we have hysteresis. So even though it was high before in this range, whatever the output is in this range, it's going to stay where it was. It's not a, this could be either one, right in that middle ground. So that's called hysteresis right there. But we dropped below 1/3 supply voltage. Now the output went high. Again, we got that hysteresis in the middle right there, unless we go above 2/3. So when we get a high input above 2/3 supply voltage, the output goes low. That's why it's inverted. And the hysteresis part is where the Schmitt trigger comes in. And I did go low enough. There it went high. But again, that hysteresis is why it's called a Schmitt trigger. That's what hysteresis means. There's a middle ground voltage where it will stay in whatever state, but you exceed the threshold voltages. So that's the upper threshold voltage, output goes low. Lower threshold voltage, output goes high. Hopefully that makes sense. And there we go. It's on the schematic there. This is a 10K trim pot. They come in other values, but it doesn't matter what value you use. It's going to be a voltage divider. So you're halfway. That is, oh, I did 6 volts right there. I actually have my power supply at 5 volts, but it doesn't matter. I just did 6 volts to make the math easy. It's going to behave exactly the same, other than the LEDs are going to be a little bit brighter. So there we go. Let's zoom back in. It makes the math easier though. as I think I got the math wrong before. I was saying 1/3 or 2/3 of the supply voltage was 3.33. I think it's 3.66. But in any case, doesn't matter. Now we're working with 6 volts. So 2/3 of the supply voltage is 4 volts or higher. 1/3 of the supply voltage, also called VCC, is 1/3 or less. Right there, 2 volts. If you're using 6 volts, makes the math easy. We could take an oscilloscope, watch those that voltage change, and then see when the output changes if we wanted to. But I've done that in earlier videos. This is just kind of more of a review. And so, in any case, I think that actually covered everything. So, if you like these longer videos, let me know. Usually I tried to make just short videos. I didn't think people liked my long rambling videos. I can do a mix of them or whatnot. Doesn't really matter. Whatever people will watch, I'll do. So, in any case, that's it. Thanks for watching.